Welcome back, 7th graders, to another Explainer. Today, we're jumping right into Lesson ID, STEM AI Seminar Unit 2, Lesson Pack 03, AI Fundamentals Worked Practice Video Overview. And the exact title for our session is AI Fundamentals Worked Practice Video Overview. I'm super pumped to dive into this with you because we're going to uncover how artificial intelligence actually works under the hood. You know, we hear about AI literally all the time, but today, we're pulling back the curtain to look at the actual mechanical gears turning inside the machine. Okay, let's dive right into this. Here's our roadmap for today. We're going to start with the big AI misconception, then look at NIST, trust and evidence, and trace the AI process. After that, we'll walk through a worked example on recycling AI, talk about limitations and human checks, and finally wrap things up with the transfer challenge. So, Section 1, the big AI misconception. This is all about separating the magic from the mechanics. Now, a lot of folks talk about AI like it's this thinking brain, right? Like there's a tiny little human sitting inside your computer. But it's really not. It's actually just a highly advanced mechanical tool. So let me ask you a direct question. If an AI sounds confident, is it always right? I mean, if you ask an AI a question and it spits back an answer that sounds literally 100% certain, does that make it an undeniable fact? It's a super tempting assumption to make, for sure. We kind of naturally think that just one successful, confident result proves the AI is perfectly reliable. And this brilliantly illustrates the massive difference between what we often believe and what's actually going on. The myth is basically that whatever goes into the AI is perfectly understood, and therefore a confident output equals a 100% reliable truth. But reality check, it's quite different. AI just mechanically detects patterns using math. That's it. And because it relies purely on those mathematical patterns, its outputs are always going to have limitations and uncertainties. It doesn't actually know things the way you or I do. It just calculates them. And guess what? Calculations can be confidently wrong. Which brings us to Section 2, NIST, Trust and Evidence. Let's ground our lesson in some hard facts. To really understand these AI limitations without just, guessing, we need to look at hard evidence from the National Institute of Standards and Technology. We just call them NIST for short. They're a U.S. government agency totally focused on measurement science and standards. And NIST created this incredibly important document called the AI Risk Management Framework, or AIRMF. Let's look at their exact definition. It's a voluntary framework developed by NIST to better manage risks to individuals, organizations, and society associated with AI and to improve trustworthiness. This right here, this is our factual bedrock for today. When we talk about AI safety, we aren't just making things up. We're tracing it straight back to this exact expert framework. According to that framework, NIST has a few core goals. They want to cultivate trust in AI technologies, promote AI innovation, mitigate potential negative consequences, and maximize AI benefits. I want to be super clear with you guys on this. This is direct foundational evidence from NIST. Their entire focus is on managing risks and building trust. In just a second, we're going to look at an illustrative, synthesized example to see exactly how these goals actually play out in the real world. All right, Section 3, Tracing the AI Process. Let's look at the actual mechanics of decision-making. To figure out if an AI is trustworthy, we really have to understand how it processes information. And every AI process can basically be broken down into this simple 4-step pipeline. Step 1 is input or data, and this is just the raw info you feed into the system. Step 2 is the model or pattern. This is the math relationship the AI has been trained to recognize. Step 3 is processing, and that's where the AI runs the input data through that mathematical model. And step 4 is the output or conclusion. That's the final result it spits out. I literally cannot emphasize this enough. The AI doesn't think about the data. It's just running data through math. Moving to Section 4, Worked Example Recycling AI. Let's take it from trash to cash. To really lock this concept into our brains, we're going to use an illustrative synthesis. Basically, a manufactured real-world scenario built entirely on those NIST foundational principles. Picture a mechanical sorting system on a recycling line. We'll call it the trash-to-cash scenario, because let's face it, if AI was actually a magic brain, it'd probably be demanding a paycheck instead of sorting our garbage, right? But this scenario is a perfect way to visualize our 4 steps in action. Let's trace this concrete recycling scenario right through our pipeline. Starting with the input, you've got sensors on a conveyor belt detecting an item's weight, its shape, and how light reflects off it. Next up, the model. The AI uses math relationships it learned to identify what pattern matches plastic versus what pattern matches paper. Then comes processing. The system simply calculates where that new sensor data fits into those math patterns. And finally, the output. A mechanical arm physically shoves the item into a specific bin based on that calculation. Notice how the AI never actually sees a plastic bottle? It doesn't understand what trash is. It's literally just processing sensor data through math. Now, what's really interesting here is what happens when things aren't perfect. Imagine a totally crushed, mangled plastic bottle comes rolling down the line. The AI has never mapped this exact weird shape before. It processes the funky sensor data, runs the math, and outputs a categorization. It might say, hey, I'm 95% confident this goes in the plastic bin, 3% paper, and 2% glass. Sounds incredibly confident, right? But what if, because the shape was so weird, the sensors misread the light reflection, and it's actually just a glossy piece of cardboard? The AI just outputted a highly confident but completely incorrect categorization. Which leads us nicely to Section 5, Limitations and Human Checks. What do we do when the machine gets it wrong? So, exactly why did the mechanical sorter fail here? Well, this is a clear limitation. The AI encountered a crushed, strangely shaped bottle it had never mapped before. Because that specific input data didn't perfectly match the mathematical model, the mechanical output was just plain wrong. Even though the math calculated a 95% confidence score, this perfectly proves our point from earlier. Confident outputs aren't automatically true. The AI is completely limited by the data it knows and the patterns it was trained on. So, how do we actually fix this? Well, we look right back to the NIST AI RMF playbook, which gives us guidance on human verification. The playbook outlines some very specific functions. While the AI mechanically categorizes based on its training, humans must map. That means identifying the risks in this specific recycling use case. And while the AI spits out a confidence percentage, humans must measure. We have to actually assess the AI system's trustworthiness by, checking the bins. Finally, while the AI sorts items, humans must manage. We have to step in, adjust the process, and fix the errors when the AI fails. Humans are absolutely required to verify that automated output. And finally, Section 6, the transfer challenge, changing the inputs. All right, 7th graders, you've seen the framework, you've traced the pipeline, and you understand the limitations. Now I want to challenge you to transfer what you've just learned to a brand new context. What happens to the AI's output if the recycling rolling down that conveyor belt is absolutely covered in thick mud? Think about those 4 steps. Think about the sensors. How does that incredibly poor data quality affect the mathematical model we just talked about? So the crucial point here is this. If the input data is covered in mud, the sensors literally can't detect the true weight, shape, or light reflection. The muddy inputs completely wreck the pattern detection. The AI's math is going to be calculating based on mud, not plastic or paper. Now, the output confidence might still seem super high, but it's going to be completely unreliable. And that requires our human evidence check from the NIST playbook to step in immediately. We have to measure that massive drop in trustworthiness and manage the system. Maybe by shutting down the whole line to wash the items before the AI even tries to sort them. The math is only ever as good as the data you feed it. You guys did a fantastic job tracking that mechanical process today. But before we wrap up this explainer, I want to leave you with this thought. If an AI's math is only as good as the raw data we feed it, who is actually responsible for a machine's accuracy? Is it the computer running the numbers, or is it the humans providing the data? Think about that the next time a machine gives you a super confident answer. Unit 02, Lesson 03, AI Fundamentals, Worked Practice Video Overview.